Hello. Today I'm going to take basic. Today I'm going to teach or revise rather very basic things about this chemical crystallography. And this course is being taught by Professor Anshuman Rajodhuri from Azhar Mohali. And today this will be the last live session for me and for you all for this semester. Like today is the live session number 13, and I am your TA from IIT Hyderabad. And my name is Sayani Burman. I'll be taking the last live session and outlining class of this course in this semester. So I would like to start with why X-ray. Like chemical crystallography is like first we should know what is crystal, right? I'll come into that later. Before that, I would like to tell you or revise you that what is X-ray. So X-rays are basically. So I'll be writing few important things over here. This are already been covered by Sir and me also from in several classes, but I'll still just revise a few things. So why X-ray? Firstly, X-ray is the electromagnetic radiation with high energy and low wavelength. There are hard and soft X-rays are also there. And so soft X-ray means lambda is the lambda value is lower, and sorry, soft X-ray means the energy value is lower, means the lambda value will be higher, and hard X-ray is energy value is higher and lambda value is lower. Then what are crystals? Crystals have the repetitive arrangement of the lattices of the image cells. Now in crystals, the typical interatomic spacing is 2 to 3 angstrom. Right. Now X-rays have wavelength of this dimension of the interplanar distance of these crystals. So X-rays are used to study the crystal structures. Now we all know Bragg's law, right? That is in lambda equals to in lambda equals to 2 scale sine theta. Now structure. Now this angle is theta, this angle is theta, this is the incident ray, this is the diffracted ray, and this is the incident angle theta. Since diffracted angle theta is this, and this is also the diffracted angle theta. But if we extrapolate this, it's what's it, incident ray, then the theta, this will be also theta. So this angle we take as 2 theta. Okay. And d is the value of interplanar distance. So the d is interplanar distance, theta is the incident angle, lambda is the wavelength of X-ray, and n is the order of the wavelength. Now coming to the next topic, that is source of X-ray. Okay. So in source of X-ray, we can say that how X-rays are got generated. So there are, okay, there is space. So let's say this is the level. This is K, this is L, this is M, this is N. Let's say from here, outer shell electron transition is happening, and it's related to small daily. Okay. And this will emit X-rays like K alpha. But the inner shell one will take generally. This is also releasing. This is the material. So outer shell transitions are associated with small daily, that is with the emission of radiations of long wavelengths. Whereas inner shell transitions are associated with large del E, the emission of radiation is of short wavelengths. So X-rays are generated by inner shell electrons mostly. Okay. We'll write here X-rays are generated by inner shell electrons. Okay. So now also there are K alpha I have written. So basically there are two types of X-rays we can see. One is this, let's say this, and this. So let's say this is lambda, this is intensity, this is 0.2, 0.6, 0. So 0.206, 1 it should be 1.0 and 1.4. This is K beta, this is K alpha. These are the characteristic radiations due to electron transitions in the atom. Okay. This we call as white radiation. Now, what can be the sources of X-rays? There are various sources or target materials. I'll just write few of them, like molybdenum, and write the here I have written lambda of K alpha radiation. Okay. So for molybdenum, it is 0.71 Armstrong. For copper, it is 1.54. For cobalt, it is 1.79. For iron, it is 1.94. For chromium, it is 2.29 Armstrong. Okay, you should always remember in this at least for this two. These two are severely used sources for the X-ray, like as the X-ray sources. Okay, so now applications of diffraction will know. So for the applications of diffraction is basically elastic scattering. Here, momentum transfer at constant energy happens, and incident energy is equals to the diffracted incident wavelength is equals to the diffracted wavelength, but incident diffraction pattern is not the same as the diffracted pattern. Okay, so I'll just write here. Here, momentum transfer also happens at constant energy, and incident uh, wavelength equals to diffracted wavelength, and but incident diffraction pattern is not equals to the diffracted pattern. Okay, and what are the applications for what are the applications of the diffraction? So the identification to identify materials or phases instances which in which crystal system the atom or the not the atom, the compound belongs to. Then determination of the structure, evaluation of order and disorder in the structure. This we'll get to know from the diffraction. Now, how I'll tell how X-rays interact with the sample. Okay, so let's say a beam of X-rays directed at the crystal interacts with the electrons of the atoms in the crystal. Now, the electrons oscillate under the influence of the incoming X-rays and become secondary source of the electromagnetic radiation. And the secondary radiation is in all directions. So the structure, like the schematic will be, let's say, this X-rays is coming. Now here it is oscillating. Let's draw a bigger one. So this X-rays is coming. This is, let's say, one single electron cloud. And this sets of electron cloud in the oscillation here. And this is sets of nucleus into oscillation. Okay, this one. So the secondary radiation, secondary radiation is in all direction now. Now the waves emitted by the electrons have the same frequency as the incoming X-rays. That is a coherent one. Uh, Oscillating charge radiates in phase with incoming X-rays. Now the emission undergoes constructive or destructive interference. You already know there are two types of interferences possible: constructive or destructive. Now diffraction from different planes of atoms produces different diffraction patterns which contains information about the atomic arrangement within the crystal. Now X-rays are reflected, scattered coherently, absorbed, reflected and transmitted when they interact with matter. Okay. So let's say, what did I just say? Let's say this is one plane, this is one plane, and this is one plane. So this is the one thing. Let's say here are atoms. Atoms are here. Now different diffraction pattern will get generated like this. Like diffractions from different planes of atoms produces different diffraction patterns. And due to mostly because of constructive interference. Now the space between diffracting planes of atoms determines the peak positions. Okay, this much is, let's say, the peak position. This much determines the peak position and the peak intensity by what atoms are in the diffracting plane. Okay, about the plane, diffracting the atoms. So, peak intensity is due to the atoms present in the diffracting planes, but peak positions is due to space between diffracting planes. Now, diffraction, you all know diffraction occurs throughout the bulk, not only in the surface. Then it takes place at all the possible Bragg angles, and only at Bragg angles, small fraction of intensity is refracted. Okay. Now, heavier atoms, like atoms with more electron cloud, let's say lead, iodine, can give every small peak. Like peak intensity will be very high. I'll just try high for heavier atoms. Heavier atoms. Okay. Whereas uh, smaller atoms or lighter elements will give low peak intensity. But among the smaller or lighter elements, hydrogen may come, but hydrogen can't give you diffraction because hydrogen, let's say hydrogen plus the proton one, it doesn't have any electrons, right? So it cannot give you diffraction. So as many X-rays enter the solid state material, it gets diffracted from multiple layer of the solid state packing, resulting in multiple patterns of diffraction. So N is derived from there only. Okay. Now there are two types of X-ray diffractions. One is single crystal XRD and one is powder XRD. Single crystal XRD is for crystalline materials or single crystals. But powder XRD is for powder crystalline materials or amorphous materials. It's because it's not always possible to get single crystals, right? Now you must know what is crystalline and what is amorphous materials. In crystalline materials means orderly array of atoms in 3D pattern, and amorphous means non-orderly array of atoms. Okay. So how does an X-ray tube work? That you should know. I'll just draw one schematic. So this one is the schematic. This is electron beam. The medium is vacuumed. This is the cathode material. This is the anode one. So this is the target material. Okay, target material like this ones, like this ones. Okay, and this is of course the X-rays. From the picture only you can get an idea. Now this is about 1 to 50 kilovolt. Okay. Now, how does an X-ray tube work? So an X-ray tube consists of a very negatively charged cathode emitter and a positively charged anode. Right, cathode and anode. Now, almost 25 volt of potential difference is maintained between the cathode and anode. Now, the cathode emitter is a piece of metal that is heated by a low voltage supply. So, electrons are liberated at the cathode by thermionic emission and are accelerated in the electric field between cathode and anode. So, there is vacuum inside in the tube, extra tube, so that cathode emitted electrons was not like can't collide with air molecules or lose energy before reaching the anode material only. Now the cathode is shaped to focus electrons into a small portion of the target material that increases intensity of the X-rays produced. Now the target is a piece of, let's say, molybdenum embedded with in a stationary water or oil, cold radiation, or on a rotating disk to prevent the anode from melting by the produced heat. It basically makes it cool down. Now, high speed electrons collide with the target and rapidly lose energy. So, there are two X-ray producing interactions between the incident electron and the atoms in the target material. So first one is electrons are scattered by electrostatic interactions with the nuclei of target material, resulting in direct emission of X-rays from the electron as it loses energy, known as the breaking radiation or the brainstorm. Now, the breaking radiation has a continuous spectrum corresponding to the electron losing different fractions of their initial kinetic energy, right? Now, when electron loses some amount of energy, like less smaller amount of energy, then longer X-rays will be produced, longer wave X-rays with longer wavelengths. And if the electron loses a large amount of energy, then X-rays with shorter wavelengths will be produced. So next is the spectrum has a minimum lambda below which X-rays are not produced. So this corresponds to the highest X-rays which are produced when the electron loses all its kinetic energy. Now the second one is takes place in the target uh, between the incoming electron and the electron of the target material. If the incident electron has certain characteristic energies, it can reject electrons from the inner shells of the target atoms. The vacancy created for inner shell electron, are filled when outer shell electrons make transitions to inner shell electrons to the inner shell, right? Hmm. Vacuum created in the inner shell, so outer shell electrons will come and fill that vacancy. Now, these transitions reduce the energy state of the atom by emitting X-rays with characteristic wavelengths. Now, characteristic spikes are superimposed on the continuous radiation spectrum to give the X-ray spectrum observed by the experiment. Now, if we change, let's say this is, if we, okay, I'll draw first, then I'll speak. We say this is the spectrum, and this is one spectrum. Okay, so there is in y-axis number of photons, and here it is energy. So basically, this is of high intensity, and this one is of low intensity. Okay, now let's say we reverse the plot. Okay, the basic shape of the plot is reversed with a continuum that rises from low energy to a peak, then falls to zero at a point where the maximum X-ray energy is received. Is- So, if the potential difference between the anode and cathode is increased, electrons gain more energy prior to the collision with the target. Now, both the height of the peaks and the highest possible energy of the X-rays increase, let's say. Okay. So, the target anode is angled to ensure that the X-rays are directed through a window in the desired direction. So, it is very controlled, like in the inside the X-ray tube, everything is manufactured in such a controlled way that only a small portion of X-ray falls on the anode and it's get detected by the detector after diffraction. And reflection also happens in a certain direction through a certain size of window. Now, what is X-ray diffraction and what is it like? The what is the use of it? Okay, let's say in an XRD experiment, a sample is, let's say in an XRD experiment, a sample is placed into the center of an instrument and illuminated with a beam of X-rays. Now, the X-ray tube and the detector move in a synchronized motion. I am sure that Sir has taught this in the very last slides about the lab experiment of the instrument handling and all. So this is from there only. I am just telling it as a story. Please do listen. Let's say, yeah, the sample is placed into in the instrument and illuminated with X-ray. Now the X-ray tube and detector move in a synchronized motion. The signal coming from the sample is recorded and graphed where peaks are observed related to the atomic structure of the sample. Now, let's say most materials are made up of many small crystals, right? So, each of the crystals, let's say each of the crystals are composed of the regular arrangement of atoms. And each atom is composed of a nucleus surrounded by electron clouds. Now, X-rays are high energy light with a repeating period called the wavelength lambda. Since the wavelength of the X-ray is, I have already just told here only, I have told that uh, the wavelength of the X-ray is equals to almost equals to distance between the atoms in a crystal. Now, a special interference effect called diffraction can be used to measure the distance between the atoms. So, interference occurs when X rays interact with each other. If the waves are in alignment, the signal is amplified. Okay, called the constructive interference. If the waves are out of alignment, the signal is destroyed, and you also know that it's called destructive interference. So now, when an X-ray encounters an atom, its energy is absorbed by the electrons. Now, electrons occupy special energy states around an atom since it is not enough energy for the electron to be released. The energy is re-emitted in the new form of X-ray, but the same energy as the original, called as elastic scattering. So now, in a crystal, a repeating arrangement of atoms from distinct planes separated by well-defined distances. When the atomic planes are exposed to an X-ray beam, X-rays are scattered by the X-rays are scattered by the regularly spaced atoms. Now, strong amplification of the emitted signal occurs at very specific angles where scattered waves constructively interfere. This effect is called as diffraction. Right. The angle between the incident and the scattered beam is known as 2 theta. You already I have shown here. If we extrapolate in this line, this one will be the 2 theta angle. Yes. Now, in order for a constructive interference to occur, the scattered waves must be in alignment, meaning the second wave must travel a whole number of wavelengths. In this case, one half of the wavelength travels on incident side and another half of wavelength travels on the scattered side, yielding one additional lambda. So, in the case of X-ray, one wavelength has traveled on both the incident and the scattered side, resulting in two wavelengths. This reinforcement occurs throughout the crystal. Now, XRD technique is used for, I just told that single crystal detection, thin films, polycrystalline mixtures of powders, or even on amorphous materials. So basically, XRD helps to develop, let's say, new pharmaceuticals, classify rock formation based on their mineral components. Let's try to understand how the arrangement of atom affects the behavior of energy storage materials and many more. Okay, so powder na- the alternative name for the powder one is we call it as polycrystalline solid. Okay, now I have already told you why single crystal XRD and PXRD is used. Single crystal XRD for single crystals and powder XRD is for polycrystalline materials, right? Now, there are two types of arrangements that we mostly commonly use, and it's very important to know. One is theta to theta type, theta to theta. So, and another one is theta theta. I'll just write next after this. So, theta to theta, the tube is fixed, sample rotates. This is the sample rotation, sample rotation, and this is detector rotation, where the source is fixed. The next one is theta theta. So here the sample is fixed and the tube rotates. Let's say this is the tube rotation and this is the detector rotation. I'll just write like this one. And here, what is fixed? The sample is fixed. Okay. Now, the Bragg-Brent geometry. This is very useful and sir has also taught us in the very last weeks. So, I'll just draw it. And I'll explain about each of the structure, whatever I'm drawing. So let's say this is the X-ray tube. Okay, X-ray is coming here, and this is with a angle. It makes omega, and this rectangular plate is called goniometer. Okay, and this makes the angle of theta, which is going to the here is the detector, and if we take the whole angle, it is 2 theta. Okay, now this amount, the space inside the circle is called the reciprocal space, and the circle, this one is, let's say, And this, sorry, and the whole thing is called evil sphere. It's on the name of the scientist, evil sphere. Okay. Omega is the incident angle and 2 theta is the diffracted angle. Okay. So it's like omega is half of 2 theta equals to theta, right? Now, let's say I'll draw one more. Let's say this is the crystal plane. Okay. And here it goes. Okay, I'll just here a cone shape happens. A cone shape happens, and this cone is called dy cone. Basically, in a powder pattern, all orientations of the crystal plane, and hence all positions of the powders are allowed. So, in a polycrystalline solid, crystals are randomly oriented and they'll produce a continuous dy cones, right? Now, the detector scans through an arc that interacts each dy cone at a single point, thus giving the appearance of a discrete diffraction peak. How the Pixartic pattern looks like, it is here intensity from 0 degree to let's say 180 degree, and this is the diffraction angle 2 theta, and your peak will look like whatever it is. Okay, these are really peaks. Now it should be sharp. So basically, what we get from peaks hardy, it's for the phase identification mostly, then determination of initial dimensions, sample purity of phase that I just told. Then the lattice mismatch will get to know between the film and the substrate, determining the dislocation density and quantity of the films, determining the thickness and all. Okay. Now, for single crystal diffraction, one thing we do extra, which is reciprocal space, using of 3D reciprocal space. A star, B star, C star, we write instead of ABC. You all must know that A equals to, oh sorry, A star equals to similarly B and C. Okay. This is for single crystal XRD only, not for powdered XRD. So what happens basically? Let's say for A, B, C, you get a peak like this. Okay. But for A star, A star, you will get a peak like this. So it will be the AWHM full with half maxima. Right. So from this, it will be easier to understand about the crystal structure. Okay. So these are very basic things. So let's start and like overall the course, not only in the beginning or in the last, but throughout the course. So the one thing I wish to tell you that when we go for the single crystal determination, if the pattern comes as in spots, let's say this just spots, then these are the uh, you are getting the diffraction from each of the atoms, right? So this is from the regular arrangement of the spots. Now, for the single crystal, it confirms you that there is one single crystal in whatever sample you have given. Uh, After the structure or the confirmation of the single crystal, you will, of course, know after solving the structure only. But firstly, you get to know about this. Now, the second one is the spot brightness relates to the structure factor, okay? And the spot position relates to the despacing, the this spacing. Now, if you get a ring pattern, let's say, so this is for powder samples, okay? Now, mm, so from here also you can detect or you can differentiate. And there are also many more patterns like amorphous patterns, like diffused ring patterns, reflecting the short and ordered structures, mostly seen for the carbon support film. Next to is Kikuchi pattern, bragg reflections of inelastically scattered electrons interfere with one another to produce bright and dark lines. So what do we know from here? Like electron diffraction is a very strong tool into investigate the nanomaterials. A small specimen is sufficient. Very thin specimens have to be used about few hundred Armstrongs. Crystals should withstand a very high vacuum and the local heating produced by the electron beam. So this is the basic of the overall concept, chemical crystallography. Now the next one is, let's say, how optical band gap, right? Optical band gap is basically the gap between the what's it, valence band and the conduction band. So right, so there are energy required to move the electrons from the valence band to conduction band by absorbing a photon is called the optical band gap. Now, there are two types of optical band gaps. One is direct band gap and one is indirect band gap. Now, energy required corresponds to direct transition in momentum, that is momentum conservation, while transition leads to light absorption and emits so as electron directly absorbs or emits a photon with same momentum like LED. Now the indirect band gap is additional change in momentum during electron transition. This simultaneous absorption or emission conserve between the energy and momentum like transistors, solar cells, etc. So this is also very important. Okay. So the next one will know that there are seven crystal systems, 14 Bravais lattices, 32 point groups, and 230 space groups. Now, among the seven crystal systems, S- there are primitive type, polycentered type, and face centered type. Polycentered here it is, face centered here it is. Like there are in the body center only in the center of the lattice there is one atom, and for face centered, like there are six faces of a cube. So in the center of each faces one atom was present. And for cubic, all the edge lengths are same. You can say for trigonal, for hexagonal, two of these parameters are same. For tetragonal also, but for tetragonal, all the angles are 90 degree. Now, for orthorhombic, none of the edge lengths are same, but the angles are same. For monoclinic and triclinic, it's very hard to be get similar. So this one is the most symmetric among the seven crystal systems, and this one is least symmetric. Okay. Then Sir has taught about the lattice symmetry or the law symmetry. So basically, law symmetry here from the chart you can say there are M3, M3 bar M, 6 by M, etc. are there. So first I'll tell you about the about each elements like M. What is M? M is mirror. 3 is for threefold rotation. Then 3 bar is for threefold rotation, and also there is one inversion sector present. Now 6 is sixfold rotation, and M's are mirror planes. Now 6 by, or here in the next one is a 4 by, means there is one, let's say, sixfold rotation or fourfold rotation, and mirror planes, and let's say this one are perpendicular to this main principal axis. Okay, similar as 2 by M. And one bar is only one inversion center present, because one fold rotation means 360-degree rotation, means you will get the indistinguishable structure only, right? So law symmetry refers to the symmetry of a crystal's diffraction pattern when it is exposed to X-rays, electrons or neutrons. It is named after the scientist Max von Laue. And also, like he also won the Nobel Prize for the discovery of X-ray diffraction by crystals. Now, in law symmetry, the diffraction pattern remains unchanged under certain rotations or reflections. This provides valuable information about the crystal structure. There are various types of law symmetry, including simple rotation and mirror symmetries, and they are categorized based on the symmetry operations that leave the diffraction pattern unchanged. Basically, you have to get the indistinguishable structure. So, understanding law symmetry is very crucial in X-ray crystallography to determine the atomic arrangement with crystals. right? And from here also, sir has gone to the stereographic projections. First, sir has taught the 2D lattice, that is like this, right? P, 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 P. Then sir has gone to the stereographic projections. Let's say this is threefold, right? Let's 120 degree. Let's say this is 1 point. If you rotate it 120 degree, it will go here. If you rotate it 120 degree, it will go here. If you again go 120 degree and inversion, then it will become like come uh, beneath the plane. So for beneath the plane, below the plane, we remark as a open circle, and for above the plane, we remark as a dot. Right. Now, similarly, here also it will be there. Here also it will be like that. For fourfold symmetry, the symbol is used as such. For twofold symmetry, it is this. For twofold screw, it is this. Now, twofold screw, this is the screw symbol. Two suffix one means what? 180-degree rotation plus half translation. So this. So what does it mean? It is 4-2. 4-2 means what? 4-fold rotation means what is the angle? 360 degree by 4 is 90 degree, but 4 suffix 2 means should be 90 degree into 2, that is 180-degree rotation plus 2 by 4. It will be just ulta. Like 2 by 4 means half translation. Right. So this is screw axis. So if you add screw and glide, uh, okay, I'll just first write that. So basically from here, from the chart, you will get to know about the point group. Point groups are what? Let's say C to V, D to D, whatever it is. Okay, for C to V means C is the like normal location. Two for twofold. V for sigma V plane. Sigma V plane means it is parallel to the enfold rotation, the principal axis. Now D to D, two for same stands for same twofold rotation, and then D is for sigma D plane, whereas the D in front, the capital D indicates that there are C2 axis perpendicular to the twofold principal axis. Right. Also, with the point groups, if you add the translational symmetry also, so you can see here only twofold rotation means what are the symmetry elements, rotation, reflection, right? So with the rotation reflection, if you add the translational symmetry, it will give you space groups. It will give you space groups. So space groups contain screw axis, which is I have written rotation plus rotation plus translation, and glide planes are reflection plus translation. Let's say this. So, so this is the atom. This is the position of a particular atom. So it will reflect, let's say it will just 180-degree reflection. Oh yeah, and this will go in half translation along, let's say this is the p direction or the y-axis. So it will come here. This is the final structure. So this is a glide plane, this one. And the glide plane is denoted as this. Sorry, this one is denoted as flu axis. Glide plane is denoted as dashed lines. Okay, let's say this will also get reflected, let's say this one, and it will translate here. So this is the final. So this is, and for screw axis, we denote screw axis as this axis. For the rotational axis, we denote as this. This is screw axis, and this is glide planes, and these are the solid lines are mirror planes. Okay, so this we have seen the variations in use in the stereographic projections and the 3D lattice projections, and also let's say there is one position XYZ. Let's say you are operating 2 by n. Okay, now twofold rotation. And we consider the twofold rotation is like the mostly the n-fold, the principal axis rotation. We consider at y-axis. Right, let's say this is y-axis, this is y or b-axis, this is a-axis, and c is perpendicular to the plane I'm drawing in. So twofold rotation parallel to the y-axis, right? So it will be x bar, y, z bar. Then mirror perpendicular to y-axis. Then x bar, y bar, z bar. Or if you do here, first you operate mirror perpendicular to y, it will be x, y bar, z. Now if we operate two perpendicular to y, it will be the same one. This one is inversion central, right? This one is also inversion. So like that you can connect, right? And if you want to try the also matrix, then you also can write like for XYZ, write 100 0 0 1 0 0 0 1. Now, if you operate two perpendicular to y, it will convert x bar, y z bar, right? So x bar means -1 0 0 0, y is intact. Then z bar means 0 0 -1. If you operate here m perpendicular to y means only y will get inverted, right? A minus sign will come here. So it will be 1 0 0 0 -1 0 0 0 1. We can say this two are inversion related, right? And if you do the absolute inversion, this will be -1 0 0 0 -1 0 0 0 -1. Right. This is a matrix method. In this method also we can solve a lot of things. So after this simple things are as short as what is like the same one. Like this is for primitive, right? So we will see P2. P4 by NNL. This 4-4 rotation is happening. So here is plus. Say 4-4 rotation will happen. Say here it is happening. So it will be this, then this, then this. Like that in the four corners it will happen. And from here you can say like a fourfold. Here I have shown now that fourfold is noted as this. Then you'll show that you'll see that this one mirror plane, this one is one mirror plane, and this one mirror plane will be getting generated. So that's how we'll get this kind of space groups. Now P is one, and if it is not P, if it is C, then there will be one more line here, and you will get one more point here, and you will get the same structure here also. So, like within the unit cell, how many equivalent positions are present, that we denote as the Z value. Okay, Z value. Like let's say this one present, 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 this one present. Right. So 1, 2, 3, 4 in the corner, and in the center there are four. So this will be eight, like that. And also we denote it as in XYZ. Let's say this one will be for XYZ for this one. Then let's say for C centering, it will be X plus half, Y plus half, and Z. See, I have already written here. We take X axis like this, Y axis like this. So this is from this position. This one is going here and then coming here, right? So x and y movement in x and y direction is happening. So that's why x plus half and y plus half is there. And if you take let's say this one, like that it will happen, and it will be let's say x plus half minus y plus half minus z. Like that it will happen, and there will be eight equivalent positions for C-centered. And for body-centered one, let's say you can say that this if this is C-centered means there is C-centering, and the one atom is present in like in the middle of this whatever I have drawn this rectangle. But for body centered also we do the same. So for should body centered also follow the same kind of things. Yeah, it will be following the same thing, but one change, which is let's say for C centering is comes for what C centering is for a center in a face, in a certain face, like two faces. Like for a cube, I've already like here also you can say that here there are six faces, right? So C centering will be let's say these two faces will be for C centering. So C centering is happening on faces only, in the center of face. Let's say this atom is this one. Right, but for body center, in here it is in very center, so it will be we have to write the Cartesian coordinate as x plus half, y plus half, and z plus half. Okay, like that. So it will change. Just Okay, and the operations will be the same thing. But when you have to determine the coordinates of body centered and C centered lattice, it will be different. Okay, this was, yeah, yeah, that's what I'm talking about, the matrix things. One means this is a 180 degree rotation plus half translation. So if the screw axis is parallel to A axis or B axis or C axis, that's how you are gonna take it. Okay. Then sir has taught about the structure factors while uh, determining the single crystal XRD structure. Now, structure factor is a quantity used in crystallography to describe how X-rays or other radiations are scattered by a crystal lattice. Structure factor. There are also atomic structure factor. F is atomic structure factor. So mathematically, the FHKL, this one, is a particular set of crystallographic planes with Miller indices HKL. So it's basically sum of J, let's say e to the power 2 pi I Hx plus Ky plus Lz. Like that we denote it. So x, j, y, j, and z, j, x, y, z are the coordinates of the atom J in the unit cell. And then HK the Miller indices for the reflection, and I is an imaginary unit. So the structure factor is used to calculate the intensity of the diffracted rays, X-rays, which is then used in Fourier transformation. This is connected with Fourier transformation, right? So, to obtain the electron density map and ultimately the crystal structure. Now, crystal structure is being solved. Raisa has taught us how to use OLEX, how to use Apex, and on how to reduce the huge amount of data sets you'll be getting from the single crystal X-ray diffraction raw data. And there are, while solving it, there are like to solve the structure, to define the structure, there are commands as shell xt, shell xl, cell xs for structure refinement, and also there are direct methods. Direct methods. Okay, I'll just do that. Least method, least square methods, Patterson methods for heavier elements and all. Now, after you solve the structure in OLEX, you'll get a result file, and from that you can transport it in a zip file with clarification files, and from that you can draw the crystal structure. Now, while reducing the data, you'll come across various factors like R int, like graphite, R sigma. This value should also like there are certain boundaries for the values, like one has to be below one or one has to be always one. Like most of all, it is equivalent to one or close to one. It is very favorable, not more than that. The chi factor is also very important. Then what's it? Mm, yeah, these are the things you should keep in mind, and your crystal should be uh, be centered, always be centered in the goniometer. It should not be only a flick kind of thing, or not having a specific dimension. It should have, then you'll get a good quality of data. Now, to get the data also, you need to fix the hemisphere. If the crystal belonging to the symmetric kind of crystal system, it will have the lesser dimension of this hemisphere. That sir has also read out that for atomic you will get octet, for cubic it will get half, like that, right? So these things are there. These things you have already been taught about. Uh, After that, sir went to the powder exciting. I have already told about it. So yeah, these are the things, and these are important questions also. I have solved many questions uh, in the 12 lectures. Please go through the videos. If you need any assistance, you can just direct um, contact us. I'll just show you again. Let's say here, ask a question, go to ask a question, and like with your Google, like with your username and password, you can ask some questions, and for problem solving sessions, you can go here and see all the videos that we have already uploaded. Okay, so these are the things you should know. So all the best for your in future endeavors and for the upcoming exam of this course. The exam is on 28th of October. Please be ready for the exam, and I hope from this course you have learned a lot of things about the chemical crystallography. So all the best for your future. Thank you.